colors slowly separating in this tube have far-reaching medical and legal implications and affect everything from the 100-yard dash to pollution detection. Actually, this is spinach, but the technique of chromatography in various forms is used to separate complex compounds into component parts and is at the center of the foofara in all forms of environmental wrangling and substance abuse. This is one of the most basic forms of chromatography, seen here as a demonstration at Seneca College. To prepare our suspicious spinach, it's mixed with methanol and mashed. Methanol is wood alcohol, and it's used here simply to make a good mash. Next, hexane is added to the mash to dissolve the components of interest. Then it's filtered and concentrated to remove the hexane, leaving basically spinach juice. Two important notes. The hexane hasn't reacted in any way with the spinach, just dissolved the components. Also, this is a well-known test subject, so we're proceeding with a tried and true procedure. An unknown substance requires more experimentation. This glass tube is called a burette. It's filled with aluminum oxide. It's like a fine white sand. A valve at the bottom controls the rate of liquid flow through the alumina powder. The burette is filled with hexane, slowly dripping out the bottom and constantly replenished at the top. A small amount of test substance is placed at the top. Chromatography relies on solvents to carry the various components of a substance through a solid medium. In this case, the solid medium is alumina, but a similar procedure uses solvent traveling across a filter paper by capillary action. Paper chromatography is one of the oldest forms of the art, but column chromatography offers a few bonuses. The solvent flow rate is adjustable, and as components separate, they can be collected from the drips at the bottom of the burette. Solvent flow through the column is constant, but the solvent itself is changed, beginning with hexane and progressing to more and more aggressive varieties. The choice of solvents has a lot to do with the effective separation of the components. Since this is a demonstration, we're collecting the colors so that they look good. In a real separation, more vials of liquid would be collected to ensure that there was no overlap of the substances. The substances extracted from spinach are beta-carotene, chlorophyll A, chlorophyll B, and xanthophyll. Chromatography doesn't actually identify these substances, it just separates them. The liquid in these vials would have to undergo further analysis and characterization to be identified and quantified. In other words, what and how much. One of the reasons that chromatography seems mysterious is that serious substance identification is done with machines that look more like this. This is a high-pressure liquid chromatograph. It functions like the column of alumina in a more automated, precise fashion. It also works with much smaller samples, down to a few millionths of a liter. The solvent is pumped under high pressure through a metal column. The column is outboard because different columns can be used for different separations. The sample is injected into the solvent and ends up separated much like our spinach. We identify the components of spinach by their color. This machine has a sensing unit that measures ultraviolet absorption, similar to color but invisible to our eyes. The UV absorption method can't directly identify substances either. They have to be identified by comparison to a known substance. This sample contained caffeine, aspirin, and phenacetin. Substituting a thing called a mass spectrometer for the UV absorption unit can give the machine the ability to identify unknown substances directly without experimentation and comparison. Brings to mind the old Christmas song, "It knows if you've been bad or good. Goodness sake."